Hello dear students, now we will discuss about properties of lanthanoids. First, oxidation states. So in general, lanthanoids, they form stable compounds in +3 oxidation state, or the compounds in +3 oxidation states are more stable. However, sometimes +2 and +4 ions solid compounds are also obtained, and this trend or this irregularity can be explained on the basis of extra stability of half-filled, fully filled or empty F subshell. For example, if we take cerium 4 positive ion, now cerium 4 positive ion, it will have electronic configuration of xenon, because 1, 2, 3, 4 electrons they are removed. 2 electrons from S, 1 from D and 1 from 4F, right? Now it has been observed that this cerium from +4 oxidation state, in order to get converted into +3, because +3 oxidation state is dominating one or more stable, so it gain 1 electron. Thereby it acts as strong oxidizing agent. Okay, and it can be seen from its value, reduction potential value for cerium 4 positive ion to cerium 3 positive ion is 1.61 or 1.74, in the range of that. Okay, now if we talk about those species which are having half-filled subshell, so europium 2 positive, again it has 4f7 electronic configuration, but it gets changed again in order to acquire that +3 oxidation state. It will release 1 electron, so thereby EU2 positive will be converted into EU3 positive plus 1 electron, and it acts as strong reducing agent. For terbium ion, same. Terbium 4 positive, it has again 4f7 electronic configuration, stable electronic configuration, but in order to show that +3 oxidation state, it will gain 1 electron and thereby will be converted into terbium 3 ion, and during this process it acts as strong oxidizing agent. So these species are having 4f7 electronic configuration, right? Then for fully filled or completely filled subshell, ytterbium is the example. Ytterbium has 4f14 and 6s2 electronic configuration. So in +2 oxidation state, ytterbium 2 positive ion, in order to get converted to +3, it will release 1 electron and will be converted to stable form, and thereby it acts as reducing agent. There are other species also, for example, promethium, terbium, dysprosium. They exhibit +4 oxidation state only in oxides, that is MO2. Okay, so these were the oxidation states of lanthanoids. Now the next property is their ionization enthalpies. In this figure, the first 3 ionization enthalpies are shown for lanthanoids, and it has been found that the sum of the first 3 ionization enthalpies of these elements was found to be similar to that of aluminium. They have almost the similarity as per that of aluminium. The ionization enthalpy values, they varies accordingly as per the size changes there, or according to their stable electronic configuration as per that. These are the values for first 2 ionization enthalpies. The previous one was for first 3, so that was found to be similar to that of aluminium, and on analysis it was found that when we related their first and second ionization enthalpies, so the value of first and second ionization enthalpies was on an average equal to that of calcium. Okay, so this shows that these have properties similar to that of alkaline earth metal. On analyzing their standard reduction potential for M3 positive to M. Again, the standard reduction potential value, these goes on decreasing in negative along the series. Okay, this trend is again similar to that of the trend we have observed in transition elements, and this depends upon their again oxidation state, ionization enthalpies, lattice enthalpy, and hydration enthalpies. This reduction potential values, when they were related, so it was found that these are almost similar to that of aluminium, but they have slight more values in negative, hence they will be more reactive than aluminium. So their properties, they lies in between calcium and aluminium. Now their chemical reactions, important chemical reactions. So starting with metal acids, they react with acids by liberating hydrogen gas. This is the same property of metals. Then with halogens, they results in the formation of halides in +3 oxidation state with general formula LNX3. With water, they react to form hydroxides, and these hydroxides, their basic character, that goes on decreasing as we move along the period. Means along the period, for example, there is lutetium hydroxide. Lutetium hydroxide is there, and lanthanum hydroxide is there. This is lutetium hydroxide and then lanthanum hydroxide. So out of these two, which one is more basic, if this question is asked? So on what basis we can explain? So hydroxides, their basic character goes on decreasing as we move along the series. Lanthanum hydroxide will be more basic than lutetium hydroxide. Reason being that MOH bond, that bond length, MOH bond length, it goes on decreasing along the series. So lutetium hydroxide will be less basic because the bond cannot be broken easily between metal and OH. Hence we can say that along the series or among lanthanoids, basic character goes on decreasing from or as the atomic number increases. Then they combine with carbon at elevated temperature to form carbides, in the same manner with nitrogen nitrides and with sulfur sulfides. With oxygen, when they are burnt in air or with oxygen, they results in the formation of oxides with general formula Ln2O3 showing +3 oxidation states. Now the uses of lanthanoids. So lanthanoids, they are generally used in the production of alloys, right? Alloy steels for plates and pipes, basically they are used over there. Then very well known alloy is misk metal. This is important. Misk metal, which consists of a lanthanoid metal, near about 95% will be lanthanoid and around 5% it will be iron, and then there might be some traces of sulfur, carbon, calcium or aluminium in between. Misk metal is used in magnesium based alloys to produce bullets, shells and lighter flints. Then mixed oxides of lanthanoids, they are also employed as catalyst in petroleum cracking, and some individual lanthanoid oxides are used as phosphors in television screens and similar fluorescing surfaces. These are the uses of lanthanoids, and in this figure this misk metal is given, and this is the composition of misk metal, iron 5% and traces of some elements such as sulfur, carbon. With this we conclude lanthanoids.